last lecture, we came up the equation in this form, and this is the solution of this system. Because the system is in decoupled form, and from the decoupled equation we can write the decoupled equation dynamics, and these are the solutions of the decoupled system. And this is the closed loop, closed form of the system in terms of the Z1, Z2, and the eigenvalues, lambda 1, lambda 2. So in today's lecture, we'll define the equilibrium point of the system of the original system, what we had before. This is the original system. And for this original system, how we can define the equilibrium point, whether it is node, whether it is node or focus, channel point, or vortex. So this is a very important topic, how we can classify the equilibrium point. So here we'll come up the different conditions for the equilibrium, for the eigenvalues. So case 1. So we are continuing from the last lecture. If, so no, first condition we can, let's assume eigenvalues are real. So under this condition, if the eigenvalues are real, we have first case, maybe subheading A, if eigenvalues are real, not complex, real eigenvalues, and distinct means they have different values, they are not same, and negative if the eigenvalues are negative. So the second order system, we're supposed to have two eigenvalues, which are already there, lambda 2, lambda 1. If the eigenvalues are real, distinct, and negative, so in that case, we can write lambda 2 divided by lambda 1, so it will be some constant because both are negative. Let's assume this is greater than or equal to 0. And from this, we can write Z2 equal to CZ1 to the power k. So this is the equation for the parabola that you know. This is the equation for parabola. So for this particular condition, if you plot Z1 versus Z2, so for example, this is Z1 and this is Z2. So the trajectory, the state trajectory will be something like this. So it is converging to the equilibrium point 0, 0. So this is, we can say, and so it means if the eigenvalues are real, distinct, and negative, so state convergence will be looking like this. And this condition we call, if you have the trajectory like that, it is called saddle stable node. It is actually stable node, not saddle, it is stable node. So this is the first case. You can try in MATLAB, you will have something like this. And second case, if the eigenvalues are real, distinct, and positive, if the eigenvalues are positive. So in that case, So for example, lambda 1, lambda 2 are greater than greater than 0, for example, greater than 0. So it means you can write lambda 1 not equal to lambda 2 because it is also mentioned distinct here, right? So if you have this condition for the eigenvalues, the state trajectories will be something like this. This is, for example, Z2, this is Z1 and Z2. So the state trajectory will be is diverging from the equilibrium point. It is not converging. So this is we call unstable node. Unstable. And if the trajectories are like this, then it is called node. And if it is converging to 0, then it is stable node. If it is diverging from the 0, then it is unstable. It is not converging to 0, that's why it's like unstable. The third case, eigenvalues are real, distinct, one positive and other negative. Okay. So in the previous case, both are positive, distinct. In the first case, both are negative, distinct. And this case, one positive, one negative, but distinct. In this case, the trajectory will be, this is Z2, this is Z1. So it will be something like this. This can be the state trajectories will be something like this. It will be looking like this. So it is called saddle point. So if you want, you can do in MATLAB, you can easily simulate this equation in the MATLAB, and you can take the different values of this lambda 2, lambda 1, and you can plot it. And so this is the, if the eigenvalues are distinct, in this case, in that case, if it is real and distinct, we have the ABC condition. And if the eigenvalues are complex, eigenvalues are complex. So in this case, it is basically under this also we have some condition. First is eigenvalues are complex with negative real part. So here basically we can assume if the lambda 1 and 2, we can say minus A plus minus IP, for example. So we have the real part is negative. And in this case, the state trajectories will be this is Z1, Z2. So it will go like this. So it is converging to the equilibrium point. There is the equilibrium point and the system is stable basically. So in this case, it is called stable focus. And second, under this section, if the eigenvalues are complex with positive real part. Positive real part. We'll take an example, it will be clear what we are doing here. So in this case, it will be unstable focus, obvious. So it will diverge from the equilibrium point. So in this case, we will start maybe here. It will go like this. So it is basically like Z1, Z2, and this is basically unstable focus. So it is means if the eigenvalues are complex, if it is there is negative real part, then it will be stable focus. If it is the positive real part, the unstable focus. Okay, just try to understand what is happening here. So this thing will be important later lectures. And C part, eigenvalues are complex with zero real part. With zero real part. It means lambda 1 and 2, we can say plus minus IB. There is no real part. So in this case, the state trajectories will be something like this. It will be, so for the defined initial condition, we have defined circle in the trajectories. It is Z2, this is Z1, so it is something like this. And this kind of condition we call vortex or center. This is how we can define the equilibrium point of the system. So based on the equilibrium point, we are coming to this conclusion, right? Because the eigenvalue is being defined from the linear system, and the linear system is linearized around the equilibrium point. And based on the eigenvalues, how the system trajectories moves in the space, and we can plot like that. Now let's take an example, then the problem will be very much clear. Let's take an example. So we'll start the system from beginning, from the linear system, nonlinear system, and how can it get linearized, and then we can study the system behavior. The question is, draw the state trajectory of the system given by y double dot plus 0.5 y dot plus 2y plus y square equal to 0. So if you notice in this equation, this is the nonlinear term, square term, right? Other terms are linear. So this is the nonlinear, and due to which the system is nonlinear. And also analyze the equilibrium points. So for this, we have to first find the linear system, we find the equilibrium eigenvalues, and based on that, we can define the, or we can classify the equilibrium point, whether it is stable, unstable, solution. So let's define the system unitative state variable form. So let's define x1 equal to y and x2 equal to x1 dot equal to y dot. And from this, we can write x1 dot equal to x2 Let us define this the function 1, x1, x2, first function, though there is no x1, but we can define like that, no problem. And x2 dot, we can define minus 2x1. If you substitute in this equation, y double dot, we can write as x2 dot minus 2x1, 2x1 minus x1 square minus 0.5 x2, and from this equation let us define this the second function f2 x1 x2. Okay, so if you notice this equation, this system, actually there is no control, the natural system, and we are studying the system whether it is stable or not. Yeah. Now to find the equilibrium point, we know how to find. We'll make this equal to 0 and this equal to 0 and find the values of x1, x2, and this will give us the equilibrium points. So let us do to find the singular points or equilibrium points or fixed point. And then different terminologies, fixed points. So we can write f1, x1, x2 equal to 0, and from which we can write x2 equal to 0. And from the second function, f2, x1, x2 equal to 0. And from this we can write from this minus 2x1 squared, sorry, 2x1 actually, and x1 squared, 0.5 x2 equal to 0. So if you substitute here x2 equal to 0, we have the equation minus 2x1, x1 squared equal to 0. And from this we have the two values of x1. One is the x1 equal to 0. Another is the or x2, x1 equal to minus 2. So the equilibrium conditions are, or equilibrium points are, we have minus 2, 0, and 0, 0. So for this nonlinear system, we are having two equilibrium points, right? So we have to linearize the system about this two equilibrium point. So we need to find the Jacobian matrix. So Jacobian matrix, we can find Jacobian matrix. We can find it J equal to, we can write dou f1, dou x1, dou f1, dou x2, dou f2, dou x1, and dou f2, dou x2. This is Jacobian matrix. So here f1, f2 is nothing but our two function. This is one function and this is another function. Right. So here let's find. So here we can find dou f1, dou x1 equal to 0, and dou f1, dou x2 equal to 1, and dou f2 divided by dou x1 equal to minus 2 minus dou x1, and dou f2 divided by dou x2 equal to minus 0.5. Now if you substitute these expressions, if you substitute this one here in Jacobian matrix, you can write J equal to, you can write 0, 1, minus 2 x1, and minus 0.5. And so this is basically, if we write in linear system form, we can write the linearized system obtained to be can write, tau x dot equal to what? Tau x1 dot tau x2 dot equal to system matrix 0, 1, -2, -2 x1 minus 0.5, and we have the state vector, which is tau x1, tau x2, right? So now here basically we can write, this is also, you can denote as A matrix, right? This is also defined as A matrix, system matrix. So now let's find the A matrix. If you notice here, this A matrix depends on x1, x1, x2, because it's a function of the states. So let's first find A, the value of A at first equilibrium point, 0, 0. We have two equilibrium point, -2, 0 and 0, 0, right? These are equilibrium points. So let's start with first 0, 0 equilibrium point. So for that, we have the A matrix is 0, 1, -2, and -0.5. And the eigenvalues we can find lambda I minus A equal to 0. And if you substitute the values, we get lambda -1, 2, lambda plus 0.5 equal to 0. And from this lambda plus 0.5 plus 2 equal to 0. And from this lambda 1 and lambda 2 is obtained to be minus 0.5 plus minus I A minus 0.25 and divided by 2, right? So if you notice here carefully, the eigenvalues are real, and they have the complex conjugate terms. So you can write here basically eigenvalues are complex with negative real part, with a negative real part. So this condition, if you go back to our lecture, so this is the condition we are having. Eigenvalues are complex with a negative real part. So we supposed to get this kind of condition. So here, if you plot, so we can have this is for example x1, x2, and we supposed to get this kind of response. And this is actually nothing but stable focus. So in this case, if you notice, this is the equilibrium point. Don't forget that. That is very important. So at this equilibrium point, the trajectory is converging to 0, 0, right? And this is basically stable focus. Now, let's work on the different equilibrium point. So now, let's evaluate the eigenvalues. Let's evaluate the eigenvalues at equilibrium point -2 and 0. So here we can directly write lambda I minus A at equilibrium point -2, 0. And if you substitute, we are having basically, I'm writing the final expression here. So equal to 0, we can write. So here from this, you can have the characteristic equation, lambda into lambda plus 0.5 is equal to 0. So in this case, if you notice, we have the eigenvalues lambda equal to 1.19 and lambda equal to minus 1.69. So these are the eigenvalues from this system. So let's look, one eigenvalue is positive, one eigenvalue is negative, and they are distinct. So this is the case. Eigenvalues are real, distinct, one positive and one negative, right? So we're supposed to get, this is the condition for saddle point, right? So we can draw the final picture. So here we have the equilibrium point, 0, 0. Another equilibrium point is minus 2 and 0, right? So here we are getting the stable focus. So we are getting something like this. So this is the converging to the equilibrium point. And another case here, we are having the saddle point. So this is the saddle point. Yeah. So this is how we can come up the state trajectory of the system. And, while we'll be doing the MATLAB, so it will connect maybe here, connect like this. So something like this, all will be connected and you'll get some formula inside this will be there, it will be there. So it can come up with a nice figure in MATLAB. If time permits, maybe in the next lecture, we'll have some MATLAB code for this. For some nonlinear function, how you can find the state trajectories of a system. Now, I'll take another example to make your another example. Maybe you can get better picture how we can come up state trajectory of a nonlinear system. So let's consider the following system: y double dot minus 0.1 minus 10 by 3 y dot square y dot plus y square equal to 0. This is very highly complex system, right? So here, study the system and classify the equilibrium points. So here we can first, let's find the equilibrium point. For that, we have to say the second order system, we have to come up with the two first order ODEs. So the solution, I'm just going some step jumps. So we can define the state y equal to x1 and y dot equal to x2. Okay. So we can write from this x1 dot equal to x2 and x2 dot equal to, we can write minus x1 plus 0.1 x2 minus x1 cube minus 10 upon 3 x2 cube. And this is, let us define f2 x1 x2, and this is, let us define f1 x2 x1 x2. Okay. And to find equilibrium point, we have to put this equal to 0 and this equal to 0, right? So doing that, we have x2 equal to 0, and from the f1, and for f2, x1 plus 0.1 x2 minus x1 square minus 10 by 3 x2 q equal to 0. And from this, x2 equal to 0. And if it is x2 equal to 0, you can substitute this x2 in this expression and also here. So we can write minus x1 square equal to 0. And from this, we have x1 equal to 0 and minus 1. So we are having two equilibrium points. The equilibrium points minus 1, 0 and 0, 0. Two equilibrium points. And this is I request you please find the eigenvalues and eigenvalues of the system and the state trajectory. So we're supposed to get the response something like this. We can verify. So response will be something like this. Diverging from the equilibrium point, this will be 0, 0. And we have another equilibrium point, maybe minus 1 and 0. In this case, it will be saddle point. Okay. So this is the saddle point. And this is, we can say, this is the unstable focus. So this is basically unstable focus because it's diverging from the equilibrium point, and this is saddle point. So I request you please verify this problem by yourself. So we have already found the equilibrium point. You can find the system matrix in the linear form. You can find the equation and you can find the eigenvalues, and based on the polarity of the eigenvalues, we can comment. So this is the structure you're supposed to get, this kind of state trajectories response. So let's stop it here. We'll continue from the next lecture on something new topic we'll have, maybe the concept will come up. Thank you.